In the last video, we found that we could express the initial wave function as a linear combination of the first three stationary states. And then in part B, what we want to find is that after a period of time, let's say time t, we know that the wave function is going to change into such a form. It's going to take on this form multiplied by some constant. And then we want to find the minimum value of t such that your wave function is going to evolve into this expression. So what we're going to do first is that we're going to express the wave function along with the t component as well. So this is not the initial wave function, we have the t here instead as well. And in order to do that, we take this expression over here. So we know that the wave function can always be expressed as a linear combination in such a form. And for the case of the particle in the harmonic oscillator, the energy levels En is given by this formula. And we know that only C0, Z1, and C2 are non-zero. For the rest of the terms, C3, C4, and so on, they're all zero. So I can express this out by writing everything out explicitly. So we have C0 times xi0, and then times e to the power of negative I E0 t divided by h bar. And then we have the second term, we just apply the same formula. So t divided by h bar, and then we have C2 times xi2 times e to the power of negative I E2 t divided by h bar. And then of course we can definitely substitute in the expressions for the e's for the energy levels. So E0 is 1/2 h bar omega, so you see the h bar that cancels out. So I can actually change this to 1/2 omega. And then we can do the same thing for here. For E1, n is equal to 1, so you have 3/2 times h bar omega. So this becomes 3/2 omega t, and the same over here. For n is equal to 2, you get 2 plus 1/2, which is 5/2. So we have 5 omega over 2 times t. So what we're going to do next is that I'm going to pull some terms out. So your wave function can be expressed in such a way. I'm going to pull out e to the power of negative 1/2 I omega t. So it seems like I left out a t over here, sorry. So there should be a t. So once I pull this term out inside the bracket, I will have C0 times xi0. And then for the second term, I will have plus C1 xi1. And then I've pulled out 1/2 of omega I omega t over here, so I'm going to be left with 1 I omega t. So I'll have e to the power of negative I omega t. And here I've pulled out 1/2 again, so I'll be left with 2 I omega t. So I'll have plus C2 xi2 times e to the power of negative 2I omega t. So this is how we can, one way we can express our wave function, complete with both parameters x and t. So I'm going to stop here for a second, and I'm going to turn your attention back to this term over here. So notice that this term, if I express this as y, which is a symbol that we defined in the last video, and then we expand this, we will get 1 plus 4y plus 4y squared. So this is just 1 plus 2y squared. And you can see that this expression is pretty much exactly the same as the initial wave function, except for this, this positive sign over here. So last time around for the initial wave function, it was some constant times 1 minus 4y plus 4y squared, and then multiplied by this e term. So if you express this whole term here as y, then your e term over here will be e to the power of negative y squared over 2. So you can see that the initial wave function was some constant times this polynomial times e to the power of negative y squared over 2. And then now, for this wave function after a period of time, we have some constant times this polynomial times e to the power of negative y squared over 2. So you see that both of these are very similar. They're only different in terms of this positive and negative sign over here. And then we know that from last time, we know that the initial wave function is proportional to C0 times xi0 plus C1 times xi1 plus C2 times xi2. So we know that because the only difference between these two terms is the normalizing constant. So that's why I used the proportional symbol over here. And you can see that because this term here takes on this form, we can deduce that this wave function after this time period of t is going to be proportional to c naught xi naught. This time it's minus c1 xi1 plus c2 xi2. So it's a minus sign because for the y term over here, which corresponds to the term that is related to xi1, now has a positive sign instead of a negative sign. So if for the negative sign you have this expression, now that you have a positive sign, you need to add back the negative sign over here. So what we know is that the wave function here, after a time period of t, it is going to be proportional to c naught times xi naught minus c1 times xi1 plus c2 times xi2. So we know that the wave function is going to be proportional to this term. And then up here, this is what the wave function is equal to after the time period of t. And so both of these terms, so that means since this is the wave function, so this is the wave function, and this is the term that the wave function is proportional to. So both of these are pretty much the same. They only differ by a normalizing constant in the front. And in this case, you can see that it's the difference comes from this t term over here. And we are dealing with a case such that after a certain time period of t, inside the bracket over here, the relationship will be expressed in such a way so that there will be no e terms in front over here. So you can see that in order for our wave function to take on this form after a time period of t, it must be the case that for that particular value of t, this term over here, e to the power of negative I omega t, must be equal to -1, so it fits this negative sign over here. And then this term, e to the power of negative 2I omega t, must be equal to 1, so that it fits this term over here. And so if both of these conditions are satisfied, then this wave function here will indeed be proportional to this term. And we know that we need our wave function to be proportional to this term in order for this condition to be satisfied, in order for our wave function to take on such a form. And so this is the two conditions that we need to consider. So I can express this in terms of sine and cosine. So I can express this as cosine omega t minus I sine omega t is equal to -1. And then we have cosine 2 omega t minus I sine 2 omega t is equal to 1. So right now we're looking for the minimum value of t such that this term, such that the wave function will take on this term. And then we know that the wave function will only take on this expression here only if these two conditions are satisfied. So what we want is the minimum value of t over here such that these two expressions are satisfied. And you can see that first of all, the I terms, since these are imaginary, and then in the end there are no imaginary terms, so we know that both of these sine terms should be equal to 0. So that gives you a hint. That means omega t must be equal to some constant times pi. And when that happens, both of these are going to be equal to 0. So now we only need to consider the cosine terms. And you can see that everything works if you choose omega t to be equal to pi. Because when omega t is equal to pi, you get cosine pi for this term, which is of course equal to -1, so it satisfies this first relationship. And then for this term over here, you get cosine 2 omega t, so that means cosine 2 pi, which is indeed equal to 1. So this condition is also satisfied. And you can see that since t is a positive number, this term here has to be positive. So this n pi here has to be positive. And so that means omega t being equal to pi is the minimum value of t such that this condition is true. So there will be other values that would also work, like 3 pi. So if omega t is equal to 3 pi, then both of these conditions will also be true. That means our wave function will also take on this form. But that's not what we want. What we want is the minimum value of t. And the minimum value is when omega t is equal to pi. And so that means the corresponding t is equal to pi over omega. So after this period of time, your wave function, which starts off with this initial form, is going to evolve into a wave function that looks something like this.